Hello friends, welcome to SemiWorld. You must be thinking what is SemiWorld? SemiWorld means semiconductor world. Semiconductor is the future because this world will be fully driven by the integrated circuits. Every smart gadget requires the IC, whether it's mobile, tablets, laptops, smartwatches, camera, automobile industry, etc. etc. This list just goes on and on. In short, all gadgets which is smart and automatic runs on IC. In this video courses, you will learn about Verilog, System Verilog, UVM, POL, and many more coding languages, which will help you to make career in semiconductor industries. Friends, VLSI Institute charge a huge amount for this full course, which is around 1 lakh rupees. But these video courses are almost free and it's worth to get into the semiconductor industries. The MNC companies like Intel, AMD, Nvidia, Google, Apple, Western Digital, Broadcom, Qualcomm have requirements of resources with these skill sets. So friends, let's get started. We will start with Verilog. It is also called hardware description language. In this video, you will learn all basic and advanced Verilog topics. For this course, prior knowledge of digital logic design is required. Please let me know in comment box if you need video on digital logic design as well. At the end of the session, you will be able to code any design spec in Verilog language, and this course will help you to crack Verilog related questions in interviews. I will provide you the problems and their solutions, and you can ask any questions and queries in comment section. Verilog sessions are divided in three parts: basic Verilog, advanced Verilog, and some useful information. Basic Verilog contains all information needed to build small Verilog models and run simulations. Advanced Verilog topics will help user to migrate from small Verilog models to large design. And useful information such as strength modeling, PLI routines, formal syntax definition will be given in part 3. Verilog has many useful features. It's called hardware description language and it's easy to learn and easy to use. It's similar to C programming language. So whoever has C programming experience will find it easy to learn Verilog. Let's see basic Verilog topics which we are going to cover. First one is hierarchical modeling concept like top-down and bottom-up design methodology. In basic concept, we will cover data types, system task, and compiler directives. Third one is modules and ports. In modules and ports, we will see module definition, port declaration, and port connections. Fourth one is gate level modeling using Verilog gate primitives. In data flow modeling, we will learn about continuous assignment, delay specification, operators, and operands. In behavioral modeling, we will learn about initial and always blocks, blocking and non-blocking assignments, generate, event, and conditional statements, branching, loops, etc. Then we will learn about Verilog tasks and functions. And at the end, we will see some useful modeling techniques. So before moving to Verilog, let's understand the whole process from writing a design specification to RTL coding in Verilog to chip fabrication. We call it typical design flow. Any design specification are written on the white paper first. Specification describes the functionality, interface and overall architecture of the digital circuit to be designed. A behavioral description is then created to analyze the design in terms of performance, compliance to standard and other high-level issues. Once the spec is ready and analyzed, we need to code the design in Verilog, which often called as a hardware description language. Along with the design, we need to do a functional verification of that design, and if we find any bug, it means mistake in the design, it will go back to the designer and designer need to fix that bug. Logic synthesis tool converts the RTL description to a gate level netlist. A gate level netlist is a description of the circuit in terms of gates and connection between them. Logic synthesis tools ensures that gate level netlist meets timing, area and power specification. If there is any issue, then it goes back to the designer and designer has to fix that design. Verified gate level netlist is input to an automatic place and route tool which creates a physical layout. Again, the physical layout is verified. If there is any issue, then either it goes back to the floor planning or designer to fix the design. Once it is fixed, it will go to the chip fabrication. So that's how chip fabrication flow is. Let's move back to first basic Verilog topic, hierarchical modeling. There are two types of design methodologies, top-down methodology and bottom-up methodology. In top-down design methodology, we define the top-level block and identify the sub-block necessary to build the top-level block. We further subdivide the sub-blocks until we come to leaf cells, which are the cells that cannot further be divided. In bottom-up design methodology, we first identify the sub-blocks that are available to us. We call it as a leaf cell. We build bigger cells using these building blocks. These cells are then used for higher level blocks until we build the top level block in the design. Typically, a combination of top-down and bottom-up flows is used in the Verilog coding. Let's take an example to understand this more in detail. As you can see, the T flip-flop is made up of D flip-flop and XOR gate in this diagram. So here T flip-flop is a top level block which will be designed from sub-block D flip-flop and XOR gate. Let's To understand the top-down methodology, let's see our first Verilog code for T flip-flop. Don't worry about the syntax. I will explain each one of them in detail later. A module is the basic building block in Verilog. It starts with the module and ends with the end module. Between module and end module, we need to write the code which will represent the design functionality. This red colored code represents the keyword. Later we will discuss about them in detail. This is the instantiation of the D flip-flop, which is the sub-block of T flip-flop. This is the module name of the D flip-flop and U0 is the instance name of the D flip-flop. And these are the connection between the ports of the D flip-flop and T flip-flop. That also we will discuss in module port connection topic in detail. And that's how we write AND module at the end. Between module and end module, we have a Verilog code which derives the functionality of the T flip-flop. And this is the Verilog code for D flip-flop. Between module and end module, we have declared the input and output ports. And in the always block, we have coded the functionality of the D flip-flop. As I said earlier, don't worry about the code right now. I will explain it in detail later. So here I was trying to explain that how T flip-flop functionality is coded by using sub-block D flip-flop. Let's go over the basic concept of Verilog. First is number specification. We can derive the values in two ways, sized and unsized. To derive the sized values, first we need to write the number of bits. In this case, which is 4, tick B stands for the binary and 1111 is the binary value. In the second case, the number of bits are 12. Tick H stands for the hexadecimal and DEF is the hexadecimal value. In the third case, number of bits are 60. Tick D stands for the decimal and 516 is the decimal value. Unsized number can be written like this without mentioning the size. By default, the size becomes 32 bits when you mention unsized value. I will recommend you to use sized values only so your code will be more readable and anyone can understand the code. Verilog supports X and Z values. An unknown value is denoted by X and high impedance value is denoted by Z. Let's take an example. 12 tick H24X. This is a 12-bit hexadecimal number. Here 4 least significant bits are unknown. Let's take a second example. 6 tick HX. This is a 6-bit hexadecimal number. All 6 bits are unknown. Third example. 32 tick BZ. This is a 32-bit high impedance number which is in binary. Now let's see negative numbers. Negative numbers can be specified by putting a minus sign before the size constant. And make a note of it that size constants are always positive. Let's take an example. Minus 8 tick D4. This is 8-bit negative number which is in decimal. 4 tick D minus 3. This is an illegal way of specifying the negative numbers. Now let's see Verilog data types. Verilog supports 4 state data types. The states are like this: 1, 0, X and Z. 1 represents logic 1 or true condition. 0 is a logic 0 or false condition. X is an unknown logic value which we have seen on an earlier slide. And Z represents the high impedance, floating state. Now let's come to the first data type, net. Nets are declared with the keyword wire. This data type is very important. You will face some interview questions related to net data types. Just as in real circuit, wire represents the connection between hardware elements. Wires have values continuously driven on them by the output of the devices. Wires are 1-bit values by default and they can be declared explicitly as a vectors. The default value of wire is Z. Wire gets the output value of their drivers. If wire has no driver, it gets the value Z. Let's see some examples. Wire A. Here wire is keyword and A is the name of the wire data type. Assign A is equal to B and C. Here assign is a continuous assignment statement. Any value change in B and C will update the value of A. We will see some rules of continuous assignment in later chapters. Next example. Wire D is equal to 0. Here value 0 is assigned to wire D at declaration. So its default value will be 0. Next data type is register. We declare it as a reg in Verilog. It represents the data storage elements. Registers retain its value until another value is assigned to them. There are two differences in reg and wire. Unlike a wire, a register doesn't need a continuous driver. The default value of reg data type is X and the default value of wire is Z as we mentioned in earlier slide. Let's see some example of registered data types. Reg val1. Here reg is the keyword and val1 is the name of the reg data type. Initial, begin and end. So this construct we will discuss later. Between initial, begin and end we are changing the value of val1. So val1 is equal to 1 tick b1. So here we are initializing val1 to 1. Has 100 is specifying the delay of 100 time units. After 100 time units we are changing val1 values from 1 to 0. Okay. So register can also be declared as a signed variable by using word sign before the name of the data type like this: reg sign 63:0 memory. So this is the signed memory with 64 bits width. Now let's come to vectors. Range and wire by default scalar data type, but we can declare them as a vectors, means multiple bit width. Let's see some example of vector data type. If wire A is a 1-bit variable, wire 7 down to 0 data, it's 8-bit data wire, or we can call it a data bus. Wire 31 down to 0, data A, data B, data C. We can declare multiple data bus like this. All three data buses are 32 bits wide. Range clock. This clock is a 1-bit register type. Range 0 down to 633 address. This is 64-bit wide address. Vectors can be declared at high and low and high, but the left number is the most significant bit of the vector, like this. Here 0 is the most significant bit of the vector, and here 31 is the most significant bit of the vector. In this slide, we will learn how we can select the part of the vector and manipulate them. Let's see first example. Wire 7 down to 0 data. This is 8-bit data bus. Data 7 is equal to 1. So here we are selecting only 7th bit, and we are assigning value to only the 7th bit. Wire 31 down to 0 data A. This is 32-bit data bus. Data A 2 down to 0 is equal to 3 tick B101. Here we are assigning the value to the 3 least significant bit of the data vector, 2 down to 0. Range 0 colon 63 address. This is 64-bit wide address. Address 0 colon 1 is equal to 2 tick B10. Here we are assigning the value to the two most significant bits of the address, 0 down to 1. In this slide, we will learn how to select the part of the vector variably. In the square bracket, starting bit plus colon width. Here plus sign indicates that part select increments from the starting bit. In the square bracket, starting bit minus colon width. Here minus sign indicates the part select decrements from the starting bit. Let's move to some examples. Here we have declared some range type vector variable. Range 511 colon 0 mem1. This is little endian notation. Here 511 is the most significant bit and 0 is the least significant bit. Range 0 colon 511 mem2. This is big endian notation. Here 0 is the most significant bit and 511 is the least significant bit. Range 7 down to 0 byte. So here we will be assigning 8 bits value from mem1 to byte variable. Okay, so here 31 is the starting bit, minus sign indicates the decrement, so it will minus the width 8 from 31. Okay, so basically it says that we are assigning 31 to 24 bits of mem1 to byte. Okay, here 24 is the starting bit, plus sign indicates that it will increment, so it will add the width 8 into 24. So here also we are assigning 31 to 24 bits of the mem1 to byte. So in these two examples, large value 31 will be the most significant bit because we have declared the variable with the little endian notation. Okay, let's see the third example. Here starting bit is 31 and minus sign indicates that decrement. So that will minus the value 8 from 31. So here we are assigning the value of bits 24 to 31 from mem2 to byte. Okay, so here 24 bit is the most significant bit because it is declared as a big endian notation. Okay, and in the last example 24 is the starting bit plus is the increment, so it will add value 8 into 24, so it will be the same 24 to 31 value will be assigned to byte. We can use the loop to select all the bytes from the vector like below. We have declared range data type mem1 in little endian notation with size 512. This for loop will select the 32 bytes in incremental manner. This for loop will start incrementing from 0 to 31. Let's say on the first loop j is equal to 0. Then starting bit will be 0 into 8 is 0. And including 0, it will add 8 bits more. Then mem1 will become 7 down to 0, which will be assigned to the byte. Okay. On the second loop, j is equal to 1. Then starting bit will be 1 into 8 is equal to 8. And including 8, it will add 8 bits more, means 15 down to 8. So that will be assigned to byte. Same way, when j is equal to 2, starting bit will be 2 into 8 is 16. And including 16, it will add 8 bits, means mem1 will become 23 down to 16, which will be assigned to byte. Same way, for loop will be incrementing till 31. So when j is equal to 31, starting bit will be 31 into 8 is 248. And including 248, it will add 8 bits more. Then mem1 will become 255 down to 248, which will be assigned to the byte. We can initialize the byte from the mem1 like this. Initializing means assigning 0 to the byte. So here if byte number is equal to 1, then it will clear 8 bits from 8 down to 15 down to 8. Okay. If byte number is 5, then starting bit will be 5 into 8 is equal to 40, and including 40 it will add 8 bits more. So mem1 will become 47 down to 40. So it will clear this 8 bits, 47 down to 40. Next data type is integer. Integers are declared with keyword integer. Default width of integer is 64 bits. Integers store values as a signed quantity. In Verilog, integer is 4-state data type. That means it can store 0, 1, x and z values. Let's see some examples. Here integer is the keyword and counter is the name of the data type. And here counter is equal to -1. So we have assigned -1 to the counter. Next data type is real. Real numbers are declared with the keyword real. Let's see some examples. Here real is the keyword and delta is the variable name. Here we are assigning delta is equal to 4e10, which is scientific value. And the second assignment, delta is equal to 2.13. So here we are assigning the real number to the delta variable. Let's define an integer I. Here we are assigning real numbers to the integer variable. So it will get the value 2, which will be the rounded value of 2.13. Next data type is a time. A special time register data type is used in Verilog to store simulation time. A time variable is declared with the keyword time. The system function $time gives the current simulation time. Let's see some example. Time, current time. Here time is the keyword and current time is the variable name. And here we are assigning $time to current time. So $time gives the current simulation time. So when you display the value of current time, it will give you the current simulation time. Now let's come to arrays. Arrays are allowed in Verilog for range, integer, time and real data types. Arrays are accessed by array name and their indexes. For multidimensional arrays, indexes need to be provided for each dimension while assigning the values. Otherwise, it would be illegal assignment. Let's see some examples. This is an array of 8 counter variables. This is an array of 32 1-bit Boolean register variables. This is an array of 100 time variables. This is an array of 4 bits wide, 8 PIDs. Each PID is 4 bit wide. This is a 2-dimensional matrix. This is a 4-dimensional array of register. This is the array of 6 wire. Each wire is 8 bit wide. Now, how we can assign the values to arrays? Let's see the first example. This represents the 8 counter variable. Each one of them is 64 bit wide. Because by default, the size of integer data type is 64 bit. Here we are assigning 0 value to the 5th counter. This represents 100 current time variable. From those, we are clearing 96th current time by assigning 0 value to that. Here we have 8 PIDs. Each PID is 4 bit wide. From that, we are assigning 0 value to the 3rd PID. Here we have 2-dimensional matrix. We are setting value 33,559 to indexes 1 and 0. This is 4-dimensional array. Here we are clearing 31 down to 0 bits of indices 7777. Let's see some illegal assignment. As I said earlier, we need to provide index while assigning the values to multidimensional array. Otherwise, it will be illegal assignment. So here with PID, there is no index specified, even though it's a multidimensional array. That is why it's illegal way of assigning values to array. For matrix, only one dimensional has specified, but matrix is 2-dimensional array. So that is why it is illegal way of assigning the values to an array. Now memories. Memories are modeled in Verilog simply as one-dimensional array of registers. Let's see some examples. Here, mem1 has 1024 location. Each location is 1 bit wide because by default rest data type is scalar. Second is memory byte that has 1024 location. Each location is 8 bit wide. Suppose we want to access 1 byte from 255th location in memory byte, then we can write like this: memory byte 255 in the square bracket. It will fetch 1 byte word whose address is 255. That's how we can manipulate the memory. Parameters. Verilog allows constant to be defined in a module by the keyword parameter. Parameters cannot be used as variables. Parameter value can be overridden at compile time. Parameters types and size can also be defined. Let's see some example. Here we have declared parameter PID with value 5. This is the parameter which is data width, which value is 256. Here we have declared sign parameter which has a 16 range, 15 down to 0. Parameter values can be changed at module instantiation or by using the def param statement, which we will discuss in detail later. Now strings. String doesn't have any specific data type. String can be stored in rich data type. Each character in the string takes up 8 bits, means 1 byte. Now let's take an example. Here we have declared one rich data type variable called string value, that is 19 bytes wide. Now we are assigning the string hello Verilog world to that string variable. Here each character of the hello Verilog world occupies 8 bits including the spaces, and total number of characters in the hello Verilog world string are 19 including spaces. So this string will occupy 19 bytes. Special characters serve a special purpose in displaying string, such as new line, tabs, displaying argument values. Here /n displays the new line, /t displays the tab, percentage displays the percentage, // displays the slash, and /double quotes displays the double quotes. Now let's come to the system task. All the system task appears in the form of dollar and the keyword. Operations such as displaying on the screen, monitoring values of signals, stopping and finishing simulations are done by the system task. Let's see the first system task, dollar display. Dollar display is the main system task for displaying values of variables or string or expressions. Let's take an example. Dollar display in the small bracket, double quotation, hello world. The format of dollar display is very similar to printf in C. A dollar display insert new line at the end of the string by default. Let's see some string format specification. Here %d displays the variable in decimal. %b displays the variable in binary. %s displays the variable in string. %h displays the variable in hex. %c displays the variable in ASCII character. %m displays hierarchical name. %v displays the strength. %o displays the variable in octal. %t displays the variable in time format. %e displays the real number in scientific format. %f displays the real number in decimal, and %g displays the number in scientific or decimal number. Let's see some example of dollar display. Here we will display the value of address in hexadecimal at time 300. Let's see the syntax. Dollar display in the small bracket in the double quotation at time %d virtual address is %h, comma dollar time address. Here dollar time will be displayed in decimal and address will be displayed in hexadecimal. Let's see the result. At time 300 virtual address is 3FE00ABC, which is in hex. Now we will display PID value in binary. Here we are assigning decimal value 5 to the PID. Let's see the syntax for the dollar display. Dollar display in double quote, ID of the port is %b, comma PID, which is the variable name. So now PID value will be displayed in binary. Let's see the result. ID of the port is 00101, which is in binary. Dollar display in double quote, this string is displayed from %m level of hierarchy. Okay, now let's see the result. This string is displayed from tbtop.l1.l2 level of hierarchy. So this dollar display is written at the L2 hierarchy. Dollar monitor. Verilog provides a mechanism to monitor the signal when its value changes. This facility is provided by the dollar monitor system task. A format of $monitor system task is similar to $display. Unlike $display, $monitor needs to be invoked only once. Two tasks are used to switch monitoring on and off. First one is $monitor on, which enables the monitoring. Second is $monitor off, which disables the monitoring. If you want to disable the monitoring, then you need to use $monitor off. Let's see the example. Syntax is like $monitor in the small bracket $time, which prints the current simulation time. In double quotation, the string is value of signal clock is equal to %b, reset is equal to %b. Means the value will be printed in the binary, then signal name, clock and reset. Now let's see how it will print when signal value changes. At time 5, clock is 0, reset is 1. So it will print the 5, which is current simulation time. Then value of signal clock is equal to 0 and reset is equal to 1. Then at time 10, clock is changing from 0 to 1 and reset is changing from 1 to 0. So it will print current simulation time. Then value of signal clock is equal to 1 and reset is equal to 0. At time 15, clock is changing from 1 to 0 and reset is still 0. There is no change. So it will print 15, value of signal clock is equal to 0 and reset is equal to 0. Here only clock has changed, that's why monitor will print the value. So at 17, $monitor off has invoked. Okay. So and after that at time 20, clock is still 0 but reset has changed from 0 to 1. Though we will not see any display here because of $monitor off. Okay. Stopping and finishing in a simulation. $stop system task. It is used to stop the simulation. $finish system task. It is used to terminate the simulation. These two system tasks are mainly used in verification module. Let's see one example. This code will execute like this. First, 0 value will be assigned to the clock. Then value 1 will be assigned to the reset. After 50 time units, $stop will invoke and it will stop the simulation. 50 plus 850 at 900 time unit, $finish will invoke and it will terminate the simulation. Now let's see compiler directives. All compiler directives are defined by using tick construct. We deal with two most useful compiler directives. First one is tick define. The tick define directive is used to define text macros in Verilog. This is similar to the hash define construct in C. Let's see the syntax. Tick define word size 32. 32 is the value. So we can use it like tick word size in the code where the value of word size will be 32. Tick define stop $stop. So here we can use tick stop, which will be working as a $stop that will terminate the simulation. Next compiler directive is tick include. Tick include will allow you to include entire content of Verilog source file in another Verilog file during compilation. Tick include is similar to the hash include in the C programming language. Now let's see one example. Here we want to include header.v file into the design.v file. So for that we can use the syntax tick include header.v, which is file name, inside the design.v file. So that's how we can include one file into the another Verilog file by using tick include. Guys, this is end of the session. In this session we have covered hierarchical modeling concept, which covers top down and bottom up design methodology and basic concept like data type, system task and compiler directives. In next session, we will cover modules and ports and gate level modeling. Thank you so much for watching this video. Please let me know your feedback, and if you have any question and queries, you can ask me in comment box. Thank you so much.